Hi there, welcome to this video. My name's John. I provide mathematics tuition for A-level maths, A-level further maths, including 6-term examination papers and mathematics admissions tests. Very warm welcome to this video where I've decided to make a video all about 1 plus 1. One of the first number facts that we learn about in our education at school is that 1 plus 1 is equal to 2. And this is arguably one of the most fundamental numerical relationships in mathematics, and of course we take it completely for granted. But why is 1 plus 1 equal to 2, and can we prove that 1 plus 1 is equal to 2? Okay, so just before we start this video properly, be warned that this is going to get quite heavy. The first bit of this video is going to seem very basic. Bear with me with it, but it is going to get heavy towards the end of in the second half of the video. So strap yourselves in. I've got some notes written down for things that I want to cover, but generally speaking, it's going to be I'm just going to be talking. I could go off in all sorts of directions. It's not going to be perfectly scripted or anything like that. A lot of it's going to be kind of ad-libbed. So just, if you don't like it, don't watch it. If there is anything that you're not sure about, if I don't explain something clearly, which is probably likely to happen, just ask any questions that you have in the comments section, by all means. If you've got anything that you want to add, I could always re-record this video further down the line if I needed to make it a bit more clear. But okay, well, let's get started anyway. So, just to be clear then, in this video, I'm going to be talking about really the usual counting numbers and the usual interpretation of addition that you learn about in your first few years of schooling, for example. Because there are mathematical structures in which 1 plus 1 is not equal to 2. And this is because the addition symbol might be interpreted in a different way, okay? Or it might be that the symbol that we use for the number 1, we're still using that symbol, but we're using it to represent something else. Not necessarily a number, okay? And these kinds of things do happen. Symbols get reused in all different contexts, and they don't always mean the same thing in these different contexts, and it's from the context that you've got to determine in a lot of cases what these symbols mean. So just to give a bit of an example, in logic, for example, so we're talking about two-value logic, then very often the symbol 1 is used to represent a truth value, to indicate that a particular proposition is true. 0 would be used usually to indicate that proposition has a truth value 0 or false. Okay, so 1 here is being used to represent effectively true. And without getting into any details about what we mean by true and things like that, we'll just accept that we know what we mean by true. If we take then two propositions and we form the logical sum of those two, or the disjunction, the logical disjunction. So we form the proposition P or Q, for example. If both P and Q have truth value 1, then P or Q will also have a truth value of 1. And what we end up with effectively is something like 1 plus 1 is equal to 1. Okay, which makes sense in this particular system, but the whole point is that the 1 that we see here, the ones that we see, don't represent the number 1 as such. They represent truth value. The plus that we see is not representing the usual addition. This is representing some kind of combination of truth values in a way. Okay, so in this particular system, 1 plus 1 certainly does not equal 2, because 2 doesn't have an interpretation in this system. I'm not talking about these cases. Okay, I'm not talking about that. I'm talking about the usual interpretations of 1 and 2 and any other number that I might use, and the usual interpretations of addition and equality. Okay, so I'm not talking about any kind of pathological or weird systems. Okay, so why does 1 plus 1 equal 2? There's a very short answer that I can give to this, and I've used this answer in a couple of other videos that I've used, and the very short answer and very unsatisfying answer, by the way, is that 1 plus 1 equals 2 because we choose it to be. Which doesn't seem very convincing, does it really? When I say 1 plus 1 equals 2 because we choose it to be, but that's effectively what it is. So that kind of suggests that maybe we could choose 1 plus 1 to be equal to something else if we really wanted. And the answer to that is yes, we could. We could develop a completely different system of mathematics, a completely different system of arithmetic, where 1 plus 1 is not equal to 2. Okay, but as we've seen, this might mean that we've got a completely different interpretation of these symbols that we use, the 1s, the 2s, the 3s, or whatever else we use, and addition. Okay. Nevertheless, I still maintain that we could, even with the kind of usual interpretations of our numbers, have a different type of addition in the which 1 plus 1 is not equal to 2. But I think, and I'm going to go into the realms of speculation here. I think that our ancient ancestors who came up with the idea that 1 plus 1 equals 2 did so for a good reason. And I think it's the obvious reason, and I'll just spell it out just so that you know what I'm talking about. So there's a distinction to be made, first and foremost, between the number of objects in a collection, say, and a number. So, for example, I might say there are 5 cows in that field. And here I'm using the word 5. And I'm using this as, according to Bertrand Russell's view in his Principles of Mathematics, which I kind of agree with, we're using the word 5 here as a kind of adjective. Okay? Because I'm using the word 5 to describe a property of that group of cows. Okay, there's a group of cows. I'm saying there are 5 of them. I'm using that word 5 to describe something about that group. Okay, but then on the other hand, we have this numeral 5. And this we use to represent this number, this abstract thing called a number that we call 5. So, arguably, this is a noun. Okay? So, on the one hand, we've got 5 as being used as an adjective, and 5, the symbol or the numeral 5, being used as a noun. And there's obviously a very close relationship that we want these to have. That is not forced to be the case. That relationship exists because we want it to exist. But they are not the same thing. 5 as an adjective and 5 as a noun, not the same thing. Okay, and it's important to recognise that. I've got some more to say. Don't worry. I've got more to say on this. It's important to recognise that we create mathematics and we choose how we want it to work. So the fact that we insist on a close relationship between 5 as an adjective and 5 as a noun is because we want our system, our particular systems, abstract systems, to work in a particular way. Similarly, 1 plus 1 equals 2. We choose that because we want things to work in a particular way. Now, maybe for the ancient folk that came up with arithmetic, originally developed arithmetic, or the rudimentary arithmetic, the want for the system to work in a particular way was probably more motivated by a need for it to work in a particular way. I would imagine that they wanted even though they might not have been explicitly thinking about numbers, 5 as an adjective and 5 as a noun and things like that, they wanted what we think of as numbers now, this abstract system of numbers, which they effectively created, whether they realized it or not. They wanted this abstract system of numbers to work in a particular way so that they could make predictions. Okay, so it had practical utility. No surprises here, by the way. This is the easy bit of the video. Things will get more complicated as we go on, but just to give an example. If I've got a group of five cows, again, using 5 as an adjective here, and I combine this with a group of 7 cows, using 7 as an adjective. So I combine. I don't add, I combine. What I obtain is a group of 12 cows. Okay? And as you're probably completely aware, if I have a group, 5 apples, and I have 7 apples, and I put them together into a single group, I get 12 apples. So the point here is that I can tell to a certain extent when two groups kind of have the same size. There's something common about them. Okay, I can kind of match things up, and I can tell that they've got the same size. So in this, got 5 cows over there, 5 apples. There's something similar about the two. And indeed, any group of 5 things. Okay, 5 trees, 5 people. There's this 5-ness that's consistent amongst all these groups. Well, I can abstract that property, and I can create this thing called 5, this number called 5, as if it were its own thing, as if it was something that existed in its own right. So we've got 5. And we can do the same for 7. And we can do the same for 12. Now, when it comes to combining things, how I combine groups of different types of objects, that might vary. But nevertheless, I can combine groups. I can combine a group of 5 cows with a group of 7 cows, a group of 5 apples with a group of 7 apples, a group of 5 trees with a group of 7 trees. I might not physically move them necessarily. Maybe the combination is a purely mental thing that happens in my head. But nevertheless, there is a process by which these groups can be combined. Well, I can abstract that property, okay, and form addition, what we know as addition. Well, what I want this, I guess this forms the basis of our arithmetic. I want this system really to help me to make predictions about things, so that I don't have to necessarily physically count the things that are there. And the things don't necessarily even have to be there for me to be able to make predictions. So I might not be around any, cats. There might not be any cats around where I am. But I might think, oh, well, if I've got 4 cats and I've got 3 cats, and I put them together, and this is all in my head, how many cats am I going to have? Well, 7, right? I expect to have 7. And I need this to be reliable and consistent. I don't necessarily need to prove anything at this stage. It just needs to be shown that this has some legitimate practical utility, that it does reliably produce results that I can make predictions according to. So I need my 5 plus 7 to be equal to 12, for example, because I consistently see that when I combine 5 things with 7 things, I get 12 things. Okay, so here the addition symbol is my combination, my abstracted version of combination. This equals is almost representing the kind of transition so to speak, from separate groups to one single. It's being considered as a single group. So in this way, I can see how the idea of 1 + 1 = 2 kind of comes about. Now, there's no necessity for me to have chosen 5 + 7 = 12. I could choose 5 + 7 to equal 25. It's just that that system now is no good for me to make predictions about things in the real world. Which, even though it's not so much the case now that mathematics is concerned with the real world, whatever we mean by that, certainly back in ancient times, arithmetic and rudimentary mathematics was valued for its practical utility. Okay, so we can see then that I can do the same thing if I've got a group of... Let me just scroll down a little bit. If I've got one thing, and I've got another thing, another one thing, and I combine these two things, I get consistently two things. So, okay, it makes sense then for me to have 1 + 1 = 2. And it would make sense for me to impose an order on numbers as well. And for me to say that 2 is the next number after 1. Because based on the fact that I don't see any instances where I add one thing to one other thing and get something other than 2. Okay. Now, okay, there are some kind of grey areas with this. So let's say I've got 5 buckets of water here, 7 buckets of water there, and I've got a big tub in front of me, and I pour the 5 buckets of water into the tub and the 7 buckets of water into the tub. I don't get 12 buckets of water. I've combined these buckets of water in a particular way to produce one big pool of water. I don't get 12 waters. Okay, so this is really based, our arithmetic, I guess, is really based on the idea that certain things, when combined from certain small groups of things, when combined into a large group, that they don't kind of blend into each other. None of them are destroyed. No new ones are created in the process. We don't see things like this. So they maintain their separation one from the other. Okay, so obviously this kind of arithmetic doesn't apply to gases, for example. Okay, I can take a volume of gas and another volume of gas, put them together. I just get another single volume of gas. I don't get 2 volumes of gas unless I somehow keep them separate. Okay, so this doesn't take Einstein to figure this out. I don't know if this is how numbers came about historically. This is entirely speculation on my part, but it seems to make sense to me. I've got no evidence that this is how things work. But one thing that I am sure about, which again we kind of take for granted now, is this idea of abstracting these properties, taking the 5-ness and creating this abstract thing called 5. This, for early man, this must have been mind-blowing. A mind-blowing discovery for early man. Whether early man realised exactly what he had done in this process of abstraction, I don't know, but it must have been absolutely mind-bending. Okay, so we see then why it makes sense for us to choose 1 + 1 = 2 if we expect our system of arithmetic to be reflective of the real world in some way. Now, of course, this number system became quite an important central feature in mathematics as it developed. Even to the present day, the system of natural numbers is a central concept. Now, mathematics is much more general now, obviously. It doesn't rely entirely on the natural number system. There are some weird number systems, very weird number systems in mathematics in general, in contemporary mathematics. But still, the natural numbers is a central feature of mathematics, and it's something that determines, to a large extent, how even our contemporary mathematics works and is interpreted. A lot of our mathematics has been developed through the properties of these natural numbers, and we don't want to lose that. We definitely, because it works, because it makes sense to us. Okay, so we definitely don't want to lose that. But the process of abstraction, I probably early man didn't have the explicit notion of abstraction in mind. Maybe they did. Now, they weren't stupid, but there is evidence that Babylonians and ancient Egyptians were perfectly capable of doing some quite complicated arithmetic. They were aware of the Pythagorean relationship in specific cases, not in its general case, but in specific cases, for example. So they could do some quite complicated arithmetic, but it was really the ancient Greeks who, in my understanding, really abstracted the concept of number and really separated number, really kind of created these, or became explicitly aware of these abstract things called numbers, and kind of detached these abstract versions from the real world interpretation. So really separated the fiveness of a group of five things from the number five, for example. It was the ancient Greeks, in my understanding, that really effected that separation. So you can read more about this in this book, Greek Mathematical Thought and the Origin of Algebra. Not for the faint-hearted, by the way. A difficult book to read, difficult book to understand. I'd be lying if I said that I completely understand it, but it's definitely worth taking a look at that. If you want to get a better idea about how the ancient Greeks kind of thought about number. You can also read T.L. Heath's various works, translations and works on ancient Greek geometry and ancient Greek mathematics. His translations of Euclid, Archimedes and Apollonius, for example. Very interesting ideas. Strange. The reason it's so difficult to understand is because their conception of number was just so totally different to the modern day idea of number. Their philosophy of mathematics was just completely different. But interesting. I'm not going to go into much detail on that. But that, to me, is where the separation really started to take place. So now, kind of moving forward a couple of thousand years, when mathematicians really started to think on a much more kind of fundamental level, certain problems started to arise in mathematics, and it required mathematicians to have a look at the basic fundamental principles of mathematics and what mathematics was effectively based on. Okay, so we're getting into what are called the foundations of mathematics here, which is one of my main interests, at least the historical development of the foundations of arithmetic, of mathematics, up to like 1950s. That's what I'm interested in. So there is still work going on in the foundations of mathematics, but it's so abstract and specialized now that I can't really understand it. So category theory and topos theory, things like this, I don't understand that kind of stuff. I'd love to understand it, but I just don't. It's far too complicated for me to understand. So what happened in the late 19th century was various mathematicians started to look at the foundations of mathematics and started to look at basing mathematics on a much more sound, logical basis. Okay, and one of the ways that this happened, and it's summarized in the book. Where's it gone? The book, The Foundations of Analysis. Let me just zoom out a little bit, actually. The Foundations of Analysis by Edmund Landau. So this is based on the work of Dedekind. Okay, this gives kind of a refined version of Dedekind's work. So the Foundations of Analysis. So I've got my copy of it here. You can probably get this online if you look carefully enough. Just saying. But also, you can find out more. I'm going to talk about this briefly in this video, but you can find out a lot more about the Foundations of Analysis, the contents of the Foundations of Analysis on my other YouTube channel, which is called The Second Number Class. I've got a series of videos where I go through in a lot more detail the contents of this book and some of the books that I'm going to be mentioning later in this video. Okay, so in this, what happens is we take the natural numbers. So when I talk about the natural numbers, I'm talking about the numbers 1, 2, 3, 4, 5, the normal counting numbers. Some people include 0. It really doesn't make any difference, to be honest with you. I'm not going to include 0 in my in the natural numbers here. I'm going to start at 1. But we take those as a given. So let's have a look. So let me scroll down. So this is where things start in Landau. We start with the axioms, okay? And we start with a set or a totality of objects called natural numbers. Right? So we take those as given. But what we don't take as given is this operation of addition. Okay? We don't even take order. When we say a set or totality of objects called the natural numbers, we haven't even imposed an order on these things yet. Okay? It's just some collection. Just like, again, cows in a field. They don't have an order to them. We can impose an order on them. We can number them 1, 2, 3, 4, 5. But they just are. Okay? So that's, for all intents and purposes, what we're taking initially as our set of natural numbers to be. And we also take a notion of equality and hence non-equality as fundamental principles. So equality has to satisfy these conditions here, 1, 2, and 3, right down at the bottom of the page, which I'm not going to go through in detail here. And this becomes our starting point. Okay, so we don't assume an addition. So we're not assuming here anymore that 1 plus 1 equals 2. We're trying to go a bit further back here. We're trying to find, we're kind of groping for what are the most fundamental principles that we can start from to develop mathematics as we know it. Okay? Now this is an incredibly difficult thing to do. And this goes part of the way. Okay? As we'll see later, we can go much further than this. But we're starting with the numbers and we're saying, okay, well, we're not going to have an order on these. We're going to determine what we mean by that. We're going to build a system, an abstract system that hopefully will lead to mathematics as we know it. Now that does mean that we need to build it in the right way, but we are building it. We build it in the way that we want to build it. Okay? Very important. There's no necessity about the way that we build our system other than we choose to build it in this way rather than that way, because there is a particular outcome in mind. So it's not done randomly. There is an idea in mind about what we want this system to do, what we want it to look like. So everything that happens when we come to defining addition, which we'll look at in a second, it's done in a particular way with that outcome in mind. So it's not done at random. So, okay, what are the axioms that our numbers have to satisfy? The following. Oh, okay, I've gone a bit far there. Scroll up. Okay, so we've got axiom 1, which says that 1 is a natural number. And interestingly, very interestingly, 1 is the only natural number that Landau explicitly states, or explicitly refers to. The number 2 never comes up, other than in the numbering of the theorems and the axiom, which that's a different thing. Within the system that Landau is talking about, the only number that he explicitly refers to is 1. Okay? Natural number. I mean. Further in, I think it does, when it proves that there is an irrational number, I think it does mention 2, but it's 2. It's not 2 the natural number. I could be wrong, but I don't think so. Axiom 2. For each x, there exists exactly one natural number called the successor of x, which will be denoted x prime. Okay, so this is kind of... It's hinting towards x primes being the next number along. But again, we don't have an order yet in our system. We don't know how to get from one number to the next, because we don't have a notion of next yet. That comes in the next chapter. No, not the next chapter. The second chapter. I can't remember. Addition comes first, and then ordering. This x primed is if what will effectively be the next number along. So it will effectively be x plus 1. Okay, remember, to get from one natural number to the next one, you add 1, of course. That's what we will effectively interpret x primed as being once we've got our addition sorted out. But there's no guarantee here that x primed is the next natural number. It turns out it will be when things are defined in the right way, but there's, just based on what we see here, that's not guaranteed. Axiom 3, we always have that the successor of x is not equal to 1. Okay, so there's what that means is there is effectively a first number. Again, we don't have an order yet, but it will be. What this will result in is a first number in our system. Again, the system is being designed in a particular way. These axioms are unquestionable. They, in the sense that they are what they are, and okay, we can question the axioms, but once we decide that we want to develop this system, then we have to accept these axioms. If we want to question these axioms, change them, then we're moving to a different system. Something that might not work in the way that we want it to. It might not even work at all. Axiom 4, if two successors, x primed is equal to y primed, then x equals y. And then we've got the so-called axiom of induction, which I'm not going to go into detail on that one. But if you have come across proof by induction, those of you that are maybe doing further maths, then this axiom is kind of based around that sort of idea. So in proof by induction, what do? You prove a statement for a base case, and then you assume that the statement is true for a particular case, and that implies the next case along. Those of you that have done proof by induction will know what I'm talking about. But it's that kind of idea. And this is taken as a fundamental property of the natural numbers, this inductive property. These axioms, by the way, are called Peano axioms. And the arithmetic that develops from this is called Peano arithmetic. So Peano axioms. Peano was a very influential mathematician towards the end of the 19th, early 20th century. Influenced a lot of philosophers and mathematicians. Bertrand Russell, for example, who we're going to be talking about in a few minutes, was in turn influenced by Frege. And these are called the Peano axioms. So once we've got our natural numbers, then we can talk about what we mean by addition. And addition is defined, it's developed in such a way so that it works, it gives the results that we want it to give. There's no necessity. So theorem 4 here, there's no necessity for addition to be defined in this way, other than we want our system to work in a particular way, and therefore this is the way that we need to do it, because this produces that kind of system. Okay? To define addition in a different way would produce a different system. But from this, we can prove that 1 plus 1 is equal to 2. Okay? So if we take property 1 here, assuming that we've done this, and I go through this in much more detail in my other videos on my other channel, if you're interested, then we get 1 plus 1 is equal to 1 primed. Okay? We define x plus 1 to be x primed, by the way. So, well, this 1 primed, we can just assign a new symbol to it. 2. We can call it 2. And then we get the result, 1 plus 1 is equal to 2. Okay? Seems a bit of a cheat, but it's not. 1 plus 1 is equal to something in our system, and we're just giving a different name to that thing. Okay? Instead of calling it 1 primed or the successor of 1, we call it 2. Okay? And in this way, we end up with a system of arithmetic that works in the way that we want it to work. So that's how Landau goes about things, based on the works of Peano and Dedekind. Well, actually, it's Dedekind's part comes in further down the line when it comes to constructing the real number system. This is really influenced by Peano. Okay. So things don't end there. Let's have a look. Where do we go from here? Next we move on to The Principles of Mathematics by Bertrand Russell. So this was published in about 1902-ish, 1901, 1902, I can't remember the exact year. Beginning of the first couple of years of the 20th century anyway. So Bertrand Russell, heavily influenced by the works of Frege and Peano. Peano's logical works. Peano had a work called, I can't remember off the top of my head, but it was quite influential in terms of developing a symbolism, an early kind of symbolism for symbolic logic that Bertrand Russell and Alfred Whitehead used in their Principia Mathematica, which I'm going to be talking about soon. Okay, so Bertrand Russell decided that he wanted to take things even further. He wanted to base all of mathematics, classical mathematics, so in other words, the usual kind of mathematics, to base classical mathematics on purely logical principles. So he thought that the most fundamental principles to take to develop a system, an abstract system on which we abstract theoretical base for our mathematics, it was logical principles that we needed to turn to. So numbers don't feature there. Okay? It's purely logical principles. So I've got my copy of Principles of Mathematics here. Again, a very difficult book to read. Very difficult indeed book to read, but well worth it if you want to get some idea about how things developed anyway. Its relevance to contemporary mathematics is obviously quite limited, but if you are interested in the historical development of the concept of number and mathematics and things like that, it's well worth a read. So in Principles of Mathematics, Russell has to construct numbers. He has to create them. Okay, so whereas before with Landau, we took the numbers as already existing, and it was really the addition and the order and things like this that we had to create. Russell goes even further back, effectively, and says, no, we're going to create numbers from basic logical principles. So how does he do that? In a very complicated way. We get to chapter 11 in Principles of Mathematics, first chapter in part 2, or section 2. And what we find is that, where is it? It's somewhere in here. Can't find it now. It's somewhere in here, anyway, in section 111, that the numbers are to be interpreted as classes of similar classes. Okay? So what do we mean by similar? A class is effectively a collection of things. I'm not going to use the word set. Now, it's the idea of class is comparable to the modern notion of set, but they're not the same thing. A Russellian class is not the same as a set. When I use the word set, I really do use this in a way that kind of hints at axiomatic set theory. And this is not based in axiomatic set theory. This is based on a completely different system. So similar classes are those which have effectively the same size. And Russell describes a way in which the size of classes can be effectively determined, or you can determine when two classes have the same size without having a concept of number yet. Okay, because in order to avoid circular definitions, there is a way to do that. I'm not going to go through it, but once you've got this set up, then you can effectively suss out which classes all have the same size. This is all abstract, theoretical, in principle kind of stuff. And then you can take all of those classes of the same size and shove them all together into a new class. Okay? And let's say you've gathered together all of the classes that effectively have threeness. So I was talking earlier about 3 as used as an adjective and 3 used as a noun. Okay, so we can recognize that all of these classes have threeness. We shove them all together into a new class, and we call that new class 3. Okay, it's a new object. That's our number now. Okay, so we can do this for all of the numbers 1, 2, 3. We can even do it for transfinite numbers, which I'm not going to get into that in this video. But once we've done that, then we can define what we mean by addition of numbers, addition of natural numbers. Once we've actually got our numbers, and again, Russell defines addition and multiplication of, although the multiplication is a bit iffy for various reasons, which I'm not going to get into. The addition is defined again in such a way that 1 plus 1 is going to be equal to 2. Okay? Because Russell is trying to formulate a system that works in the way that we want it to work. And one of the tests that we have to subject our system to, if we want it to reflect the way that classical mathematics works, is 1 plus 1 equals 2 true in this system? If not, then the system is not an accurate reflection of mathematics. It's not something that we can necessarily base classical mathematics on. It might be good for something else, or it might be useless, who knows? But it doesn't necessarily reflect, well, in fact, it doesn't reflect classical mathematics. And it turns out that Russell does this in a particular way, defines addition, and he can deduce the result that 1 plus 1 is equal to 2. Now, this is gone through in much more detail in Whitehead and Russell's later work, Principia Mathematica, which is, just so you know, one of my favourite books of all time. Seriously. And you can see my copy of it here. This is my copy of it, and you can see it's all falling apart, and it's full of my own notes and comments and things like that. You probably can't see it very well, but this is one of my favourite books. And this goes through the development, the system that Russell effectively outlines in his Principles of Mathematics, has gone through it is carried through in much more detail in Principia Mathematica. Okay, so in Principia Mathematica, it takes a few hundred pages, and it's hard work, very difficult to understand, very hard work to get through. If you are interested, I go through some of the contents of Principia Mathematica in great detail over at my other YouTube channel, second number class. So I do know quite a bit about the contents of Principia Mathematica. But what we arrive at eventually in chapter 52 is the following definition. 1 is equal to the class of alphas such that there exists an X such that alpha is equal to the unit class of X. So I'm going to explain what this means. So, X here is what's called an individual, which are our basic material in our system. They're the basic material that form our system. They're undefined, they're indefinable objects. Okay, we take them as basic objects. Alpha is effectively a class, and it's a variable in this case, effectively a kind of variable. And iota primed x, sorry, is the unit class of x. So the unit class of x is the class that contains a single member, which is x. So you can think about this, you can compare this, but it's not identical with the idea of a set with one element. Okay. So what we're saying here is that 1 is equal to the class of classes that all have one member. Okay. And then 2 is equal to the class of classes which have two members. So x and y are individuals. We're stipulating that x is not equal to y, and there is a notion of equivalence that Russell defines in one of the chapters. Equivalence between, what it means for two things to be equal. And iota primed x is the unit class of x, iota primed y the unit class of y. So this symbol here, this iota primed x, iota primed y is the logical sum of the two. So this is comparable to the union of two sets. The same, that kind of idea, but again, it's not the same idea. It's the logical sum of these two classes. So if x is not equal to y, then what we end up with is a class whose two members are x and y. So if we take any such class which has exactly two members, then it will be a member of this new class which we call 2. Okay? So once we've got that, then we come to a very famous proposition in Principia Mathematica, proposition 54.43, which there is a video about this where I explain this, analyze this and explain this in detail on my other YouTube channel. Again, the second number class. So in this proposition, 54.43, if we refer to the statement right at the end of this, from this proposition, I'll highlight it, from this proposition, it will follow when arithmetical addition has been defined that 1 plus 1 is equal to 2. So what does the proposition say? It says that if alpha and beta are members of the class that we've called 1, then this implies that the proposition that the logical product of the classes alpha and beta is equal to the null class is equivalent to the proposition that the logical sum of the classes alpha and beta is a member of the class 2. Okay, so the null class is effectively empty set, that kind of thing. logical product of two classes is like intersection of two classes. Okay. So if we find the logical product of these two classes and it's equal to the null class, remember alpha and beta are unit classes because they're members of the class that we call 1. Then this is equivalent to the logical sum of these two classes being a member of the class 2. So I'm not going to go through the proof. I've got a video on my other YouTube channel where I go through this in much more detail. Now, I'm just going to have a bit of a rant at this stage because something that really irks me is that this proposition is often referred to by people. If you look on YouTube, you'll probably find videos where that talk very briefly and in very loose terms about Principia Mathematica, and they'll often refer to this proposition. And they'll say, oh, Principia Mathematica is that book where the authors took several hundred pages to prove that 1 + 1 = 2. And they present this as if it's some kind of a joke. That as if Whitehead and Russell just had a bit of a free weekend and they decided to kill a bit of time, and they decided it'd be a bit of a wheeze to prove that 1 + 1 = 2. And this is not the case. The aims of Principia, and I get deeply offended by this because it seems to be people that have really never bothered to read Principia Mathematica and don't know anything about Principia Mathematica that kind of pretending that they know something about something that they don't know about. Principia Mathematica, I take this quite personally because it is one of my favourite works, and I think it's a very important work, very serious work. Its aims were very ambitious and very far-reaching. The aim of the authors was to reduce the whole of classical mathematics to purely logical principles. They didn't succeed. Okay, but nevertheless, the system that they produced was very rich, very complicated, but very rich, and had massive implications and ramifications further down the line for mathematics and philosophy of mathematics. The proof that 1 + 1 = 2 is a minor part. As I've said earlier, really, when you're developing an abstract system on which to base your mathematics, you can't just assume that because you've come up with something that it's going to work. You have to put it through tests. Okay? One of those tests is especially if you want your system to reflect arithmetic, usual arithmetic, then you have to show that the arithmetic works in the way that it should do. And in particular, maybe you want to show that 1 + 1 = 2 as evidence, supporting evidence to show that your system is working. Showing that 1 + 1 = 2 is not one of the main aims of Principia Mathematica. What it shows is that the system is at least working in that respect. It didn't work in other ways. Don't get me wrong, it didn't work. But at least it worked in this way. Proving that 1 + 1 = 2 was kind of a side thing. Okay, it wasn't one of the main aims. It was so far down on the list of aims that it's almost non-existent. So please don't be under the impression that Whitehead and Russell just thought it'd be a bit of fun to prove that 1 + 1 = 2 and take several hundred pages to do it. The reason it took several hundred pages to do it is because they were creating an abstract logical system to base mathematics on completely from scratch, from the most basic logical statements. That's why it took several hundred pages to do it. Anyway, rant over. If you want to find out more about Principia Mathematica and what it really involves, check out my other YouTube channel. Anyway, okay, so moving on from that then. We come on to a more modern kind of treatment of numbers, and this is the last thing that I'm going to cover. I'm taking this book, Set Theory and the Continuum Problem, by Smulyan and Fitting. So I'm not going to talk for too long about this. But what they do in this book, in a much more refined way, and they do it in the context of axiomatic set theory, which is a much more modern kind of thing, is they define the natural numbers in terms of sets, and they kind of do what Landau did. They define addition and addition. So let's take a look. How do they define? I can't remember off the top of my head. So we define the... let me scroll down. Give myself a bit more space. Okay, so they define 0, the number 0, as being equal to, by definition, the empty set. Okay, and then 1 is defined, and I'm going to write it a little bit differently to how they write it here. Okay, it's 0 plus, which is to be interpreted as the empty set union the set containing the empty set. Okay, 2 is defined to be 1 plus, which is 1 union 1. Actually, maybe I should have written that rather than the empty set. Should have written this as 0 union 0. That would be better. And then 3 can be defined as 2 plus, which is 2 union 2, and so on and so forth. Okay, and this can even be carried through to transfinite numbers. So that's on page 32, and then on page 44 we get kind of the same thing as the theorem 4 from Landau's book, where we define addition effectively. So we define a function. We show that it's an exercise in here on page 44, exercise 8.4. Prove that there's a unique function axy from omega times omega into omega, such that for any natural numbers x, and these are our natural numbers, by the way, such for any natural numbers x and y, we have that a x0 is equal to x, and a xy plus is equal to a xy plus. This is the usual addition function. I'm writing x plus y, so let me scroll down a little bit further. So writing x plus y instead of axy, we have basically our usual addition function. So, for example, we can prove that 1 plus 1 is equal to 2 in this system, because we've got that a10 is equal to 1, and 1 plus 1, using our x plus y is equal to, by definition, axy, this is equal to a of 1, 1, which, since 1 is equal to 0 plus, by definition, this is equal to a of 1, 0 plus, which in turn is equal to a of 1, 0 plus, by our properties of addition, which in turn is equal to 1 plus, which by definition is equal to 2. Hence 1 plus 1 is equal to 2. So there's all different ways that we can prove that 1 plus 1 equals 2, but it's not something we do as a joke. Okay, there's a very serious reason why there might be a need to prove that 1 plus 1 is equal to 2. Now, do we need to go this far back with our systems and things like that? Well, no, not necessarily. It's just, as mathematicians, what we're interested in is exploring the limitations of the human mind and human rationality. And so this is a very natural thing for mathematicians to do these sorts of things. Whether you need to prove that 1 plus 1 is equal to 2 really depends on what you take as your starting point. If you take the natural numbers and addition, for example, as basic principles, indefinables, then you don't need to prove that 1 plus 1 equals 2 necessarily. Maybe you follow Landau's approach and you take the natural numbers, but you don't take addition. as a fundamental principle. In which case, you need to define addition in the right way so that 1 plus 1 is equal to 2. Or maybe you take Russell's approach and you go even further back where you don't even take natural numbers as primitive ideas or primitive objects. You actually have to create them, and you have to create them in the right way, and then you have to create an addition, a meaning for addition, do it in the right way so that you get 1 plus 1 is equal to 2. But if you're going to create a system from scratch that doesn't assume the natural numbers as primitive objects and addition as a primitive operation between those two objects, then really you need to put your system to the test. And one of those tests might be checking that 1 plus 1 is equal to 2. Okay? So why do mathematicians make things so complicated? And the answer to that is because we can, and therefore we have a duty to. The job of mathematicians is to pursue ideas as far as the human mind can carry them, and to explore the limitations of the human mind and the human imagination. Because nobody else is going to do this for us. Nothing else is going to do this for us. And not even AI will be able to do this for us. Only we humans can explore the limits of our own rational mind, and therefore we must do it. Not because it's easy, but because it's difficult.